Ladies and gentlemen, I would like to welcome you on this session, high-resolution visualization. The scope of this session will cover significant issues related to visualization, transmission, as well as sharing of high-quality multimedia. We have three presentations during this session. The first one will be done by Piotr Ostapowicz from Poznań Supercomputing and Networking Center. Piotr is expert in digital circuits technology, especially connected with programmable logic devices. And he will tell us a little bit about 4K grabber, which is innovative method of data acquisition from embedded system. Please welcome Piotr.
Hello, thanks for a quick introduction. Okay. Okay, can I go to the full screen? Thanks. First of all, it's the first time for me to stand before such noble audience, so I am a little bit nervous, but I will try to make a good presentation. First of all, let's try to briefly summarize my presentation. We will go in the first part through the project objectives. I will tell something about motivation for our job. I will tell about decisions that were made. Then we will go to a consideration about possible ways of performing the 4K live streaming, because our decision wasn't the only one possibility in that case, but we decided to go that way because of some facts, and I will try to give a closer look on this. The Future Internet project, to be exact, our work is a part of the Future Internet project, and I have to say a few words about it. Research, maybe research is a big word here, because as a matter of fact, we are a group of engineers that are working with electronic digital circuits. But of course, we obtain some results. We go to some deductions, and I will show or tell something about the results of our work. Benefits, disadvantages, of course, something has to be told about it. And step forward, the last part of my presentation is connected with the vision for the future and the future of our system. Okay. The networking research capabilities. Well, one can say that networking field has nothing to do with our job, with subjected job, but as a matter of fact, it has, and I will try to tell you why. First things first, PSNC, as a matter of fact, is an operator of the Pioneer network. I think that fact is well known, but the network is built, it contains about a few thousands of kilometers of fiber links. It is based on network equipment of the highest optical technology. It involves DWDM technology. It creates a great possibility for scientific purposes. Excuse me. And as a matter of fact, 4K approach is such purpose. What do I think? Well, we are continuously trying to combine network capabilities with another technologies, and 4K approach is here a good example. Well, when it all rised up, I mean, well, 4K technology rised up. The natural vision that was created in minds of my colleagues was to build something unusual, something with the highest possible quality. I mean, the 4K live streaming, for example. It is not a secret that 4K technology creates a great possibility of visualization. We can just imagine a camera that actually is observing some, for example, medical surgery. We can imagine a group of students or medical experts that are far away from that place, about thousands of kilometers, and are watching a razor-sharp picture with highest possible quality of details. Well, a challenge, very, very interesting option, but unfortunately, 4K technology is closely connected with Digital Cinema Initiative's proposal, which exactly makes some assumptions for future cinema. 4K technology was defined there, and as a matter of fact, most of the equipment for 4K market is dedicated to cinematographic purposes. So we have these projectors, we have cameras that are in some way incapable of doing some things that are interesting from our point of view. For example, a digital cinematographic camera is not equipped, usually is not equipped with full resolution live streaming interface, because from the point of view of a camera operator, it is just useless. Camera operator, cinematographic camera operator is interested in taking a footage, and his work will be available after many hours of post-production. So we had to consider a few ways of. We were very interested in making live streaming, but it was difficult because there were few ways to go, and first was connected with dedicated design. I mean, we considered the possibility to build our own camera, but the image sensor was the biggest problem. It is very hard to get a proper image sensor with proper electrical interface. And also, what is very important here, it is hard to adapt it in custom design. So we had to resign from building the camera. Another possibility to perform a 4K live streaming was to make a hardware hack in cinematographic market product. It was too risky because, well, what do I mean? There is a data path between image sensor and internal digital logic of camera, and there should be some points when we could connect our digital circuitry, but it is very easy to make a distraction of equipment, so we decided to resign from that option. And the last, most interesting from our point of view option was to make a live streaming without hardware impact provided to the device. Well, as a matter of fact, each camera that actually is able to record content onto mass storage actually performs a live streaming in some way, locally of course. But if we build some device that will act as mass storage and will perform some actions in the background, we will be able to make our live streaming. Of course, you have to know what exactly is put down on the mass storage. And that was the biggest problem, because the producer of camera wasn't interested in sharing information with us about the proprietary standards, formats, etc. So we had to get those information in the way of reverse engineering. And we did it. That was the base for our work. The Future Internet project, well, it is a base for our job. And PSNC takes a part in most of work packages there. It involves 90 teams from 90 institutions in Poland, like it is written down. There are two key ideas. First is to promote IPv6 protocol, because it is not a secret that we run out of IPv4 addresses, and there must be some replacement for it. Of course, IPv6 is ready, but not promoted enough to use it. Another idea, another conception is connected with so-called parallel internets, where network is virtualized and used by few conceptions of transmission. And one of the conception is connected with the live streaming project. Okay, and here we go. This is the prototype. I think that, no, it was presented on last year Terina conference, actually. Well, we, after putting all together that those facts that I mentioned about, we decided to build our own device, which is equipped with mass storage interface. It can be seen on the left of the PCB printed circuit board. As a matter of fact, it is a simple listener. It is based with the most important part in the prototype is the FPGA device, and the most important logic is actually softwired into the FPGA device, and it is a simple listener. So when camera is recording the content, it listens to it, making a background processing, and put the data out through the USB in high-speed mode. We decided to use USB. Of course, 1 gigabit Ethernet would be better, but it was hard to get proper integrated circuits. Disadvantages, well, of course they are. And the biggest problem, after a few months of work, of course, we made something stable. We made a device that actually can perform live streaming using our conception. And in this case, the biggest problem is with visible artifacts. I mean, the image distortion. It is caused by the fact that actually camera is not writes down only the useful data, but also its system has to maintain the operation, the file system of the storage. So there are random sequences of data that contains actually data structures dedicated to file system. In this case, it is FAT32. So there are some situations where camera has to close the file, open another file. There are going some information about data name, etc., etc. It is mixed together with useful data. Our softcore, which exactly produces the R3D file, creates R3D file and puts it into a PC station, and that is the reason why visible artifacts comes out. Of course, we know how to cancel it. We know how to fight with that problem. It is caused by a simplified file system analyzer, which exactly is a part of FPGA design. But unfortunately, we ran out of FPGA resources. And we had to make an improvement concept that will be described in further part. Another problem is that a single processing pipeline of the Red Rocket is a hardware accelerator of Red Company. When it is fed with distorted data, it will start to produce distorted picture for random amount of frames. And the conclusion here is that the only way to make it stable is to produce clear data without any corruption. And of course, I will tell about the solution for this. Another disadvantage is the bottleneck. Well, we choose the USB transmission because assumptions are that USB can give us about half gigabit per second throughput. But as a matter of fact, reality wasn't so merciful for us, because we were able to achieve about half of that speed. And that was obvious that with such throughput, we will not be able to produce 4K full resolution live streaming with our prototype device. Single path pipelining, well, as I said, our device is just a simple listener, and when it processes a single frame, well, camera will not wait for finishing of the job, so another frame will be just lost. The conception is to put another pipeline, of course, parallel to the first one, but like I said, we ran out of FPGA resources, so we have to leave the prototype device as it was. Well, the improvement concept. We decided to use faster, bigger, more capable FPGA device. As a matter of fact, new families of FPGA devices produced, for example, by Xilinx, are equipped not only with logic resources like slices, flip-flops, etc. There are some useful logs like gigabit transmitters, clocking resources, etc., etc. So it is very interesting. Of course, they are also expensive, but oh well. We decided to use it. We decided also to use development board, because it is a quick way we considered it as a quick way to get results. Chosen development board is actually equipped with 1 gigabit Ethernet interface, so we were able to eliminate the problem of the bottleneck also. The SATA standard analysis, well, compact flash interface actually isn't natively supported by Red 1 camera. Actually, there is a daisy chain between camera logic and the mass storage device, and central element is a simple converter that acts as that just makes some conversion between serial ATA standard and ATAPI, parallel ATA standard. So we decided to take a closer look on the SATA to figure out if it is possible to make some useful work with it. And it occurred to us that it is very flexible. It gives us higher abilities to control the flow of the data. And fortunately, new generation FPGA devices are able to support this standard. We decided to go this way. Well, there are two approaches. First is connected with transferring the model of our prototype to a new platform, and there are two controllers, customized controllers connected back to back with a central element that is put between them, that makes analyze like our prototype device and sending down the data to put it through the Ethernet interface. But this model is a little bit complicated, because when master side receives the frame from the initiator, it just assumes initiator or master side assumes that it is ready for another frame. So there are such problems like collisions, and etc., etc. And another approach is a little bit different. We decided to shift the processing to the cloud, because all the time I was talking about black box approach. I mean, there is some device that is connected to a camera. There is some processing made in the field of electronic device, and there is some data output. But when we will be able to shift the processing to the cloud, I mean to outside, we could get an interesting solution, because in that way we don't have to focus on particular device like Red One camera. We can consider that there will be possibility to connect our system to any device actually that is equipped with serial ATA interface. And we are actually trying to develop all those two approaches simultaneously. Okay, things to do. There are always some problems with clocking frequencies of our FPGA device, because those frequencies are very high, so our logic have to be optimized as it is possible, because with unoptimized designs, we are quickly going into problems. Well, I must say that the hardware part is actually ready. So we have to develop a sensible software. It is a must. And warranty of flexibility, like it is said for other grabbing purposes. In the final device, we are going to make full 4K processing to get full resolution of the live streaming without those problems that I mentioned. There will be no artifacts, because in second approach, the processing will be shifted to a cloud, and we will be able to quick develop the software. Making a software is much easier than producing a hardware or designing a hardware. We assume that compatibility with new RED products, new cameras, will be possible. Okay, the future. As a matter of fact, few interesting premieres are incoming this year. I mean, JVC, Sony, and Panasonic are going to release new cameras capable of producing 4K material, capable of producing of live streaming. And this is a good and a bad information in one, because first of all, it proves that our research was correct. I mean, there is a group of people that need live streaming. Second, or bad news is that our work actually is maybe useless, but that's not true, because like I said, there is another point of view to our system. And we can use it in another solutions. Of course, we have to remember that there is a group of people that owns expensive equipment unavailable to produce live streaming. So I think that our system will be useful for them. And that's it, I think. So if there are any questions, feel free to ask.
Hi, a couple of questions. In the first attempt to creating this board, this FPGA, you mentioned that you tried to use the USB interface, the USB bus for the. Was this? Could you say if this was using synchronous USB or something else, or the problem was the burstiness or something related to that? Because I have had some personal experience with that sort of thing, especially with synchronous USB. And the second question is, so you're effectively streaming. I want to stream in whatever format that the red cameras are recording to in their internal disk. So this is probably proprietary. Mm-hmm. Could you just elaborate how you envision to further use this at the other end, at the receiver end, beyond the simple perhaps scenario of having a receiver, decoder, and display for live streams? I mean, what other applications could be done, considering this is a proprietary format for?
So you are asking if we can, I don't know, spread the device?
No. You said that the other end is should be probably software processing.
That's right.
Other tools do you have tools, or have you developed tools? Are there tools to process this proprietary RED format?
Well, we are thinking, we think that we are able to build a system that will be quite open. And the most difficult part will be shifted to FPGA device, and the rest of the work will be performed on the PC station or in the cloud, like I said. So to put it in another way, any problems with proprietary standards, etc., will be solved in the software part.
Okay. So you will be solving this by developing software. There are no ready-to-use tools for working with RED formats.
Well, we have a framework, I would say so, but there's a lot to do.
What about the USB?
About the USB, the biggest problem is that selected transceiver actually can run or can be configured for work in different modes, and selected mode by us was, not proper. Okay. Any other questions? Okay. So thank you.
Thank you very much, Piotr, for this interesting speech. Our next speaker is Frédéric Noël, who is professor of University of Grenoble, the Institute of Technology in France. Frédéric leads a European research infrastructure about visualization and interactions, and he will tell us about network requirements for ultra-high definition within a visualization infrastructure for research. This is the Visionaire project.
Well, thank you very much, Mr. Chairman. Ladies and gentlemen, it's a pleasure for me to present you this presentation about requirements for a network like Visionaire, which is a visualization infrastructure for research, quite new infrastructure. So let's just tell a few words about what is Visionaire. Visionaire intends to be a world-class European infrastructure about visualization. That means that we expect to open access to a large research community to promote excellence of a European research by providing virtual and material services in the field of visualization. I believe that visualization may be a good use case for ultra-high definition networks, and it's why we can expect to find the requirements from this visualization infrastructure about networking. It is a 4-year project nowadays, starting in February 2011 and finishing in January 2015 under the scope of a 7 framework program. However, we are expected to become a sustainable facility. What are the resources provided by Visionaire? Visionaire provides 4 types of dedicated resources. First, resources for scientific visualization, resources also for ultra-high-definition rendering, 4K, 8K facilities, as we spoke just before. We have also facilities about virtual reality and facilities about collaborative environment and augmented reality. And obviously, we provide also services through the internet in order to provide knowledge about visualization technologies and methods. At this time, we have 29 facilities which are distributed in Europe. You can see the name of these facilities, which belongs to several partners, various PSNC, also in these providers, working about ultra-high definition network system. All these facilities must be connected, and we need to interoperate between all these facilities. How we can provide access? We open a permanent call for project, and we already received 45 project proposals in 2012. We expect almost 40 more in this year. When a project is accepted, Visionaire partners will support the training on each specific facility, will support video conferencing and e-learning session for these visualization technologies, and we will also have a budget for accommodation and logistic support for the guests of Visionaire. Every research group led by a European or associated country researcher may be eligible for access to visualization and interaction methods in Visionaire whenever he provides a frontier research program with non-commercial research issues. That means that the results must be public, since it is public money from the European Commission. Obviously, you are welcome to propose projects if you are interested, but it is not the topic of this presentation today. The project can come from any kind of applications, anyhow. My purpose is clearly that we are on distributed infrastructure. You can see the partners which are widely distributed over Europe. We have 25 partners, 12 countries, I said before, 29 installations from all over Europe. And obviously, interoperability will be a key challenge for us. But interoperability means a lot, and we have to undertake and to see what are the requirements for such an infrastructure about networking. First, interoperability means and expect interconnection, and obviously we use the European networks to do so. And we have specific members in the consortium which are directly connected to the high bandwidth network, the dark fiber, with PSNC, University of Twente, University of Essex, I2CAT, which are directly connected to these systems. And we have to discuss for every kind of applications the bandwidth which will be expected and the latency which will be expected for the application we want to apply. The second point about interoperability is to be able to provide awareness about what we propose. And we develop for that a EU resource map to get a free access to the knowledge about the facility we have. It is based on an ontology system, and we are developing this ontology system to get an easy navigation through resources. Obviously, it's not easy to create this ontology itself, because it is the first time we try to make a catalog of all the facilities in Europe about visualization and interactions technologies. At this time, this ontology provides a detailed catalog of facilities. We can see all the devices owned by all the partners, the technical points about these elements. And I just want to highlight that this catalog will be open for external applicants, and it will be possible in a few time to provide other information than the partners' information in this catalog. And for the moment, we are not fully aware to model interconnection capacities and to see how we can interconnect these facilities. We have a device list, that's nice. We have many links between the partners and the device and the project that can be handled in this ontology. But we need also to solve an issue in order to demonstrate how we can interconnect these facilities. And it's still a problem under discussion. Third point, interoperability means content sharing, usually. And we have two main solutions, streaming solutions for with high bandwidth, when high bandwidth is expected for video streaming or audio streaming. But we can expect also remote model control. That means that the model must be first uploaded offline and few parameters are shared online when we need to work on remote location. And in this case, low bandwidth is expected in this case. Or there's something which is on the bottom. That means that we can mix both solutions, obviously. In any case, the main parameter for us is low latency. We expect to have low latency, even if we can work sometimes offline rather than online. We may connect many devices. We have a few of them here. We can connect holographic screens, stereoscopic viewers, virtual reality caves, like the one on the left. It's the biggest one in the world, which is settled in Ria, but we have also other caves, more traditional caves. We can have also collaborative environments, or multi-touch tables, and obviously high resolution visualization technologies like 4K, 8K system. The solution to connect these devices depends mainly on the context of usage. So I will pass some context in order to show the requirements for every context. First, the augmented collaborative environment context. We call this context where we associate augmented reality technologies, multi-touch table, holographic screen or displays, collaborative environments, but also stereoscopic viewing system whenever collaboration is expected. In this case, I will just take an example which is quite meaningful, I believe. If we want to create telepresence with holographic technology, holography is quite new. We have here a screen which is in my lab in Grenoble, an holographic display, where we have a very good resolution in 3D, 9.8 megavoxel. It is a display from the Holographica company in Budapest. But the high resolution for each eye is only 500 per 300 pixel. It's very amazing technology because you can look around the object without any glasses and you can handle the object directly, like I do it on this image. The technology is based on 20 video projectors with quite classical resolution. If we want to extend this technology to go towards 8K resolution, which is far from the technology today for every eye, we will need about 1 terabytes per second in order to have a fluent telepresent technologies. If we want to do it with video streaming over 20 video projectors with resolution, with expected resolution. Obviously, this will not be easy with a 10 gigabytes technology, which are spread in in every institute right now, and they will need better networks facilities for this. We have also the virtual reality context. In this context, we share mainly caves, like you can see here, a cave in the University of Kaiserslautern, a cave in the University of Stuttgart, and on the right, a cave of the University of Mediterranean, which are 3 by 3 by 3 caves with good resolutions. Even this resolution will be extended, I believe, in the future. We face several challenges, which are the same as for augmented collaborative environment. The main challenge is the size of a digital mockup. We need for that new interaction models, and new devices are expected. If I take an example just for an Airbus A380, we have in a digital mockup, we have 350,000 parts that must be modeled, and we must navigate inside these elements. If we want remote connections to the digital mockup, you see that the networking facility will be very impressive also to do so. But also we have other challenges, which is mainly the deployment of technology. If I show you again the cave the inertia cave in the INRIA Rennes, which is a four-sided cave, even if there are two walls shut down on this photo. It is the largest one in the world. It is a big building in order to create these elements, and it's not so easy to deploy. I really believe that 4K and 8K will be deployed faster with this kind of technology. And even if we can also extend the resolution within this kind of caves. So here are some examples of new devices expected for virtual reality. In any case, for virtual reality, since we have virtual scene, it is for the moment and currently usual to preload offline the model and just to share some parameters about the evolution of the scene directly online. So it is the way we will be able to face this issue right now. The third context is about scientific visualization, where we address tools, which can be virtual reality caves, stereoscopic screen, and so on, to navigate into scientific results and huge data sets. We have two main cases in scientific visualizations, which are due to the source of data. The data can come from scientific instruments, tomography, camera, telescope, or any observatory of nature is available in this case. And a second case where the source of data will come from simulation. In the first case, we will use mainly streaming solutions because visualization and image is the main things which is scanned. In the second case, the volume of information is defined by some million or billion of finite elements. The units for the simulation process is in teraflops, and we know that we go towards exascales technology very soon. In this case, offline preparation of the visualization will be required because we cannot be sure to be able to visualize in real time all the results of this kind of simulation. Even if we can expect live interaction with the simulation if we want to have the human in the loop of the simulation sometimes. So it will be a great challenge to solve this point also. So for scientific visualization, we mainly have offline simulation whenever simulation is expected, but we will have to go towards streaming solutions also. And maybe we can also try to minimize this effort of sharing content by simplifying the results. It does not make sense for an analyst or a scientist to have millions of degrees of freedom in simulation results in order to handle this in a visualization screen. The last context is clearly dedicated to this session with ultra-high definition network, where we could focus on tools and methods to visualize high-quality images. We want to allow to share high-definition image and fields over very high bandwidth networks, and we need to be independent, to have independent solutions or usage on the network. Here you have on the bottom rooms from University of Essex and from I2CAT, I believe, where we have 8K and 4K solutions. The scenario is quite always the same. We have a real-time rendering system which sends the data to a streaming server, which is sent through the network to a high-resolution visualization facility. We can expect on the other side to have a control from the remote visualization system of a real-time rendering system. Well, we can have some specific facilities to provide that. Here on the bottom left, you have a 3D stereoscopic system in with 4K resolution in the Postnam Super Network Computing facility. We can have also the virtual lab of the University of Twente, which can be connected. I2CAT, USX also. We expect a real-time remote high-resolution visualization through the network in this case. And obviously, the streaming solutions are mainly expected since we mainly provide image with the challenge about codec translation, real-time rendering, and we always need very high bandwidth in this case. So let me go to the conclusion. The summary is that we need, for this kind of infrastructure, network connections. It is obviously mandatory. We need for that also to be able to aware about our systems. And we have two major modes for content sharing, online streaming and offline model behavior. But we should also consider many topics like security issues. We have many difficulties, many pragmatic difficulties to open ports through network connections when we have low bandwidth connections only. We need also to have interoperability between software. Up to now, even if in our short consortium, we have almost 6 or 7 or 8 solutions to interconnect virtual reality scenes in our systems. And we have to go towards standardization of these elements with common protocols and development of common formats. Maybe format exists, but we have to promote one and to be sure that it is used by every partner inside Visionaire and maybe outside Visionaire after that. And we have to address also format translation in this case for streaming codecs, but also for virtual scenes. At last, interoperability is, for me, also at a higher level of abstraction, and we will need to find standard metaphors for interactions in remote cooperation. We will need also to address the translation from discipline point of view, discipline models, towards visualization applications. So, just a last word, you can participate to this effort by applying project, and we will be very happy to host your project if you propose project in this infrastructure. Thank you very much for your attention. I can answer questions if any. No question? Well, fine.
Thank you for this presentation. We had now our last presentation by Petr Holub. Petr works in Institute of Computer Science of Masaryk University in the Laboratory of Advanced and Networking Technologies, and he is also a researcher in testnet. He will tell us about GPU compression in ultra-grid platform.
That's right. Can you hear me?
Yeah, I can.
Yeah, you can. That's not surprising. Because we're standing next to each other.
You can.
That's super. That's much better. Okay, so I'll be the only one now standing between you and your lunch. So I'll try to use my 30 minutes to entertain you a little bit. I just need to check. Yeah, it looks like it's the latest version of the presentation. Super. So I'll be speaking about GPU compressions in the ultra-grid platform, as was indicated in the title of the presentation, and utilization of this platform for medical applications. So my presentation will be sort of split into two parts. One is the technology part, and the other is our experiences with the medical platform and deployment of the platform in the medical community. So How many of you have seen in the past uncompressed high definition over IP? Raise your hands. I mean, I've been in a business. I've been in a business for a number of years, and we have done a number of demonstrations. With nowadays technologies, with nowadays networks, it's not a problem. Can you do uncompressed 4K over IP networks? Again, how many of you have seen uncompressed 4K over IP? Well, fewer people do, but still, technologically speaking, 4K video with 422 subsampling, you can easily run it over 10 gigabit network. It's mere 6 gigabits per second in 4 times HD SDI format. So again, it's not a problem. But is it no problem indeed? I mean, how many production deployments have you seen in the past? How many of you were successfully able to deploy these technologies at your institutions? How many of you have 10 gigabit networks up to the very edge of the network? How many of your users inside your institutions and the institutions that you are serving as national research and infrastructure networks, how many do have such an equipment? And even if they had, and even if we are able to send these flows from the edge of the network, what would this do to our backbone networks? And currently, we still have many of those links running 10 gigabit per second. We have some 40 and 100 gigabits per second network links, but with 1.5 gigabit per second per 1 HD uncompressed stream, it can still be very disruptive technology, especially if there are many streams that come at once into the network. So from my perspective, I've been in uncompressed HD over IP business since 2005, I guess. And it's been a depressing perception a little bit to see how hard we pushed this technology through and how small the community remains. So this is why about 3 years ago, I started a group of PhD students which focuses on utilizing GPU architectures, which is something fairly affordable for most of your users, to do high performance, low latency, interactive compression schemes, so that we can utilize what is readily available in your networks. That's mainly gigabit network infrastructure. Probably most of your users do have either 100 megs per second or better 1 gigabit links down to the very endpoints. And to figure out what we can do with the commodity hardware. So technically speaking, we need, when speaking about high interactivity and high quality, what does this mean? It means high image quality, it means low latency, it means it has to be affordable for the users. For instance, in those medical communities where I'll be talking about, if we try to push even some H323 hardware to these communities, it's sometimes hard because the equipment is expensive, and many clinicians will think twice before buying such an equipment because they also need to buy equipment for them to treat the patients. And this is their priority. Video conferences are not their priority. This is very nice to have. This is perfect for conciliary purposes. This is perfect for education of their students. But it's a secondary goal. So it has to be affordable. And last but not least, it has to be simple to use and simple to deploy. I mean, there is usually no advanced technical staff at the hospital or even at many universities. They struggle with having advanced people supporting their daily work. So what does high quality mean first of all? In terms both of the video and audio quality, it's defined by the senses of the users. If you are unable to distinguish between uncompressed video and compressed video, it is definitely sufficient to have such a quality of the compression. And this is basically our goal in the UltraGrid platform. We want to have compression as good as being undistinguishable from the uncompressed video. Of course, sometimes because of further capacity constraints, we need to resort to lower compressions. But still, this is the goal. You can fairly easily verify this using so-called discrimination tests. I mean, how many of you here in the room do hi-fi audio in their homes? Well, there are a few people. Many of you may know that this is almost kind of a religious community sometimes. Those advanced hi-fi guys, they do all sorts of stuff like demagnetization of CDs in order to achieve the perfect magical sound. And one of the banned words and banned principles in this magical community is ABX tests. ABX tests is one of the basic discrimination tests. You let the user hear one version of the video, say uncompressed, or uncompressed video. Let him see the compressed version. And now we run a series of randomly chosen compressed, uncompressed. And the user has to tell, is it uncompressed or is it compressed? And if in 10 cases, when running 10 cases per experiment, if they miss more than once, that means we're below 95% probability or 95% certainty that they can distinguish between those two versions, A, B. So this is something that we conceptually use to assess suitability of the platform for various applications. What does interactivity mean? Again, it's defined by the senses of the users. We have a standard I2T G114, which is about one-way transmission delay for telecommunication purposes, basically. And it states that if we are below 150 milliseconds, the environment should feel perfectly interactive. For many applications, and it was surprising to me, especially in the medical communities, that even for advanced applications like remote control of DaVinci robots, they're able actually to tolerate much higher latencies. They're able to accommodate close to 200 or even sometimes 300 milliseconds of latency. They just slightly modify their habits, how they hand over instruments during the operation, but basically they can accommodate. Of course, there are some environments, especially in arts, like chamber orchestras, where they can tolerate much less. For chamber orchestra, it's said to be between 10 to 20 milliseconds of latency that can be reasonably easily tolerated. So this defines the goals that we're shooting at with the UltraGrid platform. We're not targeting the chamber orchestra, obviously, because we want to stay with the commodity hardware. There are other solutions like LoLa for Cessnet MVTP for K-Box for those who seek latencies below 10 milliseconds. And this requires either a dedicated hardware solution, as in case of the MVTP box, or it sacrifices something. As in case of LoLa, it sacrifices the video quality to achieve the ideal audio low latency behavior, even for a chamber orchestra to collaborate over LoLa. So in our case, we want to have an affordable platform for high-quality interactive image transmissions using commodity hardware. Commodity hardware for us means PCs, currently Linux PCs, but we're also now thinking about porting the platform to Windows, and Mac platform. We use commodity video cards. Part of our work is done using portable GLSL language, which basically works on any modern OpenGL supported graphics card. Part of our work is done in CUDA, which requires NVIDIA cards. So if you want to run those more advanced things, go for NVIDIA cards as of now. We use commodity video capture cards. This is another part that limits that gives the lower limit on the latency, because commodity capture cards mostly work by handing us individual frames, handing over individual frames, so you can get the video line by line, as in case of dedicated high resolution. And if the user has 10 gigabit Ethernet network available down to the end box, it's perfect, but it should not be necessary. The software is open source. It's readily available from the website. And it has many applications in medicine, in arts. That's something I forgot to mention here, in cinematography, in education. It can transmit, or it can transfer the data between many pairs of sources. And this is just a simple example from Baranov Studios, where we're transmitting from dual link HDSDI to dual link HDSDI for some post-production purposes. But basically, we can take many more inputs, like HDMI. This is now available on many cameras, and it was already mentioned in a first talk of this session. There are new cameras that are showing up on the market that can do even 4K using HDMI, 4 times HDMI. It's called Quad HD. And I've just checked the price at BH Photo, and the JVC camera with 4 times HDMI out with Quad HD resolution costs like $5,000. So it's becoming affordable. We can do component composite, HDSD. We can do even screen capture in case that you have some kind of visualization and you need to transfer it over the network. So we can use OpenGL to get the screen as a video source. And we have a number of video outputs. We can output over any stuff which we used for the input, provided that the capture card is full duplex or it supports output operation. But we have also other options to display. We can use computer screen. We can use Sage for tile displays. And we can use specialized display filters. This is the case where we used special display filter. This is a Sage-based tiled stereoscopic screen, which was on demo at Supercomputing last year by Planar Systems. And it basically works like each of the video or each of the screen line has a polarizing filter in front of it, and the lines are interleaved in a way that you have a line for the left eye, line for the right eye. So we have developed a very simple GLSL filter that basically takes those 2 images for left and right eye, merges them together into a single image with interleaved lines, and display it on a screen like this without any problem. This is another visualization from last year's Supercomputing. This time it's running over a larger Sage wall, running different compressions, basically giving user compression comparison, which I'll be showing in more detail just a few slides later. In terms of video resolution support and video format support, we support 2K, HD video in both 422, 444 subsampling. Mainly the 444 subsampling is important in case you have some specific computer-generated imagery. We do support Super HD or Quad HD. This is something interesting with the new JVC cameras. We support native Super HD or 4K, for instance, with Kona 3G card. We have full support for the audio, including native interfaces to ALSA on Linux and Core Audio on Mac OS X. So no intermediate levels of abstraction are needed anymore. Though it's still sometimes useful to use, for instance, Jack, which has very broad deployment in professional audio installations. And we also can take or play out using embedded sound, which comes either through HDMI or HDSDI. So if you have a camera which produces both video and audio through HDMI, we can take both, and we can play out both. if you run it on a television. And the platform works in full duplex mode, so it can basically, a single machine can do both sender and receiver. In terms of compressions, which is the main focal point of this talk, we currently support 3 different compression schemes, 2 DXT compressions, DXT1 and DXT5. Both of them are being basically color indexing compressions, color indexing schemes that are relatively trivial compared to Jpeg, which we have also available. It's not Jpeg 2000, it's normal Jpeg or motion Jpeg. We have forward error correction. Currently, in release candidate 3, which is available on the website, we have shifted multiplication and XOR-based error correction. And for the release candidate 4, which should be released in a few days from now, I hope it's by the beginning of the next week, we will have integrated the LDGM, low density generation matrix forward error correction, which is one of the most advanced forward error correction schemes. So hopefully this will provide much better ratio between redundancy of the information and the capability of correct multiple errors occurring in a same data block. We have a graphical user interface with persistent parameter storage. So you can choose a video source and video display device and all the configuration parameter, and there are quite a few of them which you can choose from and store it persistently across the sessions. And we have a Qt version which is for Linux and a native version for Mac OS X. This is just what a GUI looks like. It's fairly simple. You have a configuration screen here. Here you just specify this is the advanced window for the configuration. The simple window is just specify your sending address and hit the button send, and it keeps going. And this is just a window that displays log information, basically reporting the number of frames per second that we were able to successfully send or receive. This is the same stuff on Mac. So currently supported platforms are Linux. We test or we develop primarily on Ubuntu. So if any of you come with a question, what Linux distribution shall I use? I mean, it doesn't matter that much, but if you want to get as close as possible to what we use for the development, we use Ubuntu. We support Mac OS X in versions 10.6 and 10.7. So Snow Leopard and Lion. We provide source distribution, and with each major release, like 1.1 is the upcoming release, we also provide binary distribution. Because there are just a few users on Mac who can work with the source distribution, we want to provide a binary distribution for the release candidate 4 on Mac as well. So, getting to the compressions themselves, the DXT versus Jpeg. The DXT is fairly simple, and we focused on portability as much as we could. So basically, you can run it even on your laptop computer. It's where the OpenGL is supported, the new enough OpenGL, it should work. The Jpeg requires much more computational power, so that's why we opted for CUDA. In terms of DXT performance, the DXT1 provides fixed ratio 1:6. That means for 1.5 gigabit per second 1080p video, you get down to 250 megabits per second. This clearly gets into the gigabit Ethernet range and works reasonably. The quality of DXT1 is not what I would call superb, but for many purposes it works. And we have actually 2 implementations of DXT1, CPU-based, which is quite old now. It's available since, I think, 2008, and it it shows significant artifacts because of relying on integer optimizations. And we have a new implementation on GPU which uses floating point arithmetics, and it surprisingly corrected many of the problems of the CPU version. We have DXT5, which outputs twice as much data, basically, and therefore it's just 1:3 compression ratio. But the main point is this compression is really, really very good. So for half a gig, for 1080p video, you get really superb video quality. As for the throughput performance, we get something close to 800 megapixels per second for DXT1 on GPU and 600 megapixels for DXT5 on GPU. High performance commodity GPU. Basically, if you divide it by 2, because you have 2 megapixels per 1080p HD image, approximately, you get the throughput in frames per second. So we get like 400 frames per second for HD in DXT1 and about 300 frames per second for DXT5. As for the JPEG performance, this is a bit more complicated because JPEG is a smart compression which depends on the type of the image that goes in. If it has high frequencies inside, it provides worse compression ratio. It's more computationally demanding. So that's why you will see some ranges where I speak about the compression performance. In general, another parameter what the compression depends on is the quality settings of the JPEG, denoted as Q parameter. And generally, we recommend using Q equals 52, Q equals 95, depending on the target applications. Generally, Q above 90 is really, really hard to distinguish, or close to impossible to distinguish for a viewer. We did a number of ABX tests, and there are only very specific patterns where you can actually tell the difference. So in terms of the compression performance, we get even higher than for the DXT, but the trade-off here is use of the CUDA platform. So we're dependent on NVIDIA there. And also, it's worth noting that the decompression part is actually slower than the compression part. This is because of the characteristics of the JPEG decompression of Huffman encoding and decoding. To give you a visual perception of the differences between the compression, this is a full HD image, so 1920 times 1080. And we will take just that small window out of the image and enlarge it for the whole screen so that you will clearly see the differences. But bear in mind, it's highly enlarged. So this is the uncompressed video. I mean, just notice the background and notice the edges of its optical fibers, by the way. So this is what happens when you compress it to DXT1. I mean, looking that close, it obviously sucks. You can see that there is huge noise on the edges, and the background on the top right is heavily posterized. And just to give you, this is the difference. Now for DXT1 on GPU, this is something which I've mentioned already. There is a significant improvement. This is the CPU version. This is the GPU version. This is much, much better. Now, this is the DXT5 version. And now we're very close to being undistinguishable from the uncompressed version. So this is the uncompressed again. So this is the DXT5. This is the uncompressed. You can see a slight amount of blur in the image, but it's not very significant. And bear in mind, it's highly enlarged. And this is JPEG quality set to 90. So again, compared to the uncompressed, there is you can see some noise around the edges. some high frequency noise around the edges, but it's not very well. You can also see some smearing of details in the background, but again, it's highly enlarged for one-to-one viewing. Close to nobody was able to distinguish. So, in terms of the bandwidth we get for the JPEG, it really depends on the content. So this is arbitrarily chosen. We've chosen an image with high frequencies, so this goes like an upper limit of the bandwidth that is required for the quality settings. So you can see we can easily get even below 100 megabits per second if needed. And for practical applications, for real-world images without those high frequencies, we can get even half of that bandwidth, and you need to test it with your applications or with your image sources. This is just an idea to give you an idea of how fast is the compression inside the GPU. This is the GPU part only. You can see that in many cases we're around 1 or 2 milliseconds per frame for HD video, and the blue line is for 2K or Quad HD. This is the whole chain going with both CPU and GPU part. There is also some CPU processing involved, especially in the formatting of the stream, and obviously there is some overhead of transmission of data from the processor memory to the GPU and back. So this performance includes everything. And this is PSNR description of JPEG performance with respect to the quality and the compressed image size. What is interesting on this image is this part, because you can see that going from about 90 quality, and quality is set to 90, the image size ramps up dramatically. So you can experience fast increase of bandwidth required for the transmission if you go above quality set to 95. In terms of the latency measurements, basically this is the schematics of the measurement. We achieve like 2 frames per second of latency on perfectly commodity hardware. It means about 67 milliseconds at 30 frames per second. With the compressions, we have an increase of half a frame or 1 field or 1.5 field for JPEG. And it's still perfectly interactive. It's actually quite surprising when you're tuning audio between cities, for instance, for some transmission. You have somebody over a cell phone, and you hear, once the audio starts coming, you will hear the audio from the cell phone coming at least 100 milliseconds after what gets through the ultra-grid platform, simply because cell phones have higher latency, and we can get much better. And you can hear not a reverberation. You literally see second voice coming. That means that it's above 100 milliseconds of latency. Another important thing is how affordable can we get. We can use machines which cost about $1,000. This is fairly affordable. Cinegrid workshop this winter, or last winter, saw a demonstration of 4K video playout on a machine for about $1,000. For $500 for the machine itself, $500 for a high-performance commodity card. And we're currently working on trying to squeezing this into even smaller package like mini ITX boxes, but we're currently struggling with this, and I'll mention it at the end of the presentation. So getting back to the medical applications, this is I'll demonstrate it on a transmission which we did for a 12th anniversary Congress of Czech Cardiology Society about 2 weeks ago. And we had like 3 operations there. This is the open heart surgery. Basically, they are replacing an aortic valve in a heart. So This is what the UltraGrid can be used for, or was used for successfully. And why should we care at a Terina conference? For me, primarily, this is because medical community is a large research community, and they need video transmissions both for research purposes and for educational purposes. For some applications, they require real high quality of the image. We'll see it in a demonstration, in this demonstration, but it's important to bear in mind that for other purposes, they're fine with what comes in H323 equipment, 6 megabits per second. So we always need to think twice before recommending the high-performance solution to such a community. And we need to have good reasons to do so. With the UltraGrid, we need to be aware of a few things. They usually have 100 megabits per second or a gigabit network to the end hosts, but they usually do not have 10 gigabit network backbone in the hospital. So we always need to discuss with the technical guys at the hospital to make sure that we're not exceeding the capacity and we're not tampering regular backups, for instance, that they have from various instruments into backup storage. And sometimes traffic shaping is needed in order to make sure that no harm is done. There are various sources in hospitals usually, and if you do a transmissions like this, please be aware that sometimes the instruments have non-standard interfaces. For instance, with those open heart surgery or with those angiology heart operations, we were said, okay, it should be no problem. We have a composite video here coming from the X-ray machine. Well, it is composite video, but it has 1249 lines per image, and it has 10 volts level. So it's not anything that you could easily capture using any commodity capture card. Another thing, and this is real imperative, is to make sure we minimize the load on the physician. It was visible during the demo which we had at certain point during this operation. This is the angiology operation. They basically inject a probe into your groin and go all the way to your heart, do the operation remotely there, and return the probe back from through the groin. And it was, we could literally see at a certain point something went wrong during the operation. And it was like 20 seconds of silent panic in the operating room because they have many people who watch such an operation, and it should go well, and they absolutely have no brain left for any transmissions. So this has to be as invisible as possible. And generally what helps is if we were able to install these technologies permanently into their operating rooms, into their seminar rooms. And this is something which already started to happen, at least in the Czech Republic. Because they want to have live view. I mean, the chief clinician wants to have a preview of what's happening in the room for some consulting services, for instance. And if they get used to it, it's much less stressful when they do it for some huge demo or a huge PR event or whatever. In this case, in case of the angiology, they're basically operating under a weak X-ray, and the whole image is just different shades of gray. And if it gets compressed through like H323 equipment, for some of the doctors, it's not acceptable. We know that there are some transmissions over H323 equipment in the world, but at least the more advanced doctors at the cardiology congress, they just said this is no go for us, and we waited with transmission of the operation until you come with a platform like the UltraGrid, so that we can transmit it in a sufficient quality. We did a simple ABX tests with the doctors, And we figured out that quality of 90 or above is clearly undistinguishable for all persons in test. For some persons in tests, even quality of 70 was not distinguishable. DXT5 is undistinguishable for most, and DXT1, this is the other extreme, was distinguishable for the most persons in a test. This is how it looked like. Basically, you can see that the quality 90, even with doubling for forward error correction, we were getting only 160 megabits per second. This is just to show you the dependence on the content, because this is a normal real-world content. So we get about 80 megabits per second for the single stream at quality of 90. And we were also transmitting back from the venue to the operating rooms at quality 50. And it works superbly. And you can use UDP packet reflectors for this, as we were using since 2005 to implement multi-point video transmissions, even compressed or uncompressed. So this is just to show you the images they're working with. You can see electrical probes, stimulating probes that are inside the heart through the groin. And this is what they need to operate and need to discuss, and they need to clearly see what they're doing during the transmissions. And this is, again, the open heart surgery. Basically, we had 2 angiology operations and 1 real. This was, according to the Cardiology Society, this was first transmission implemented over the internet of open heart. Means we literally had a camera sitting on top of the operating table looking on the heart. So this is about the experiences which we have with using ultra-grid and an example of deployment for the medical communities. So basically, what you should take away from this talk is we can do really high-quality transmissions, undistinguishable or very close to undistinguishable from uncompressed video at data rates of from 80 to 200 megabits per second per flow. You can do it with perfectly commodity hardware, commodity GPUs, commodity PCs or Macs. And it should be affordable, and we would love to see, and I think that our community needs to see much wider deployment of these technologies, be it ultra-grid or something else, than we had so far in the last 7 years or so. Because that will be the real success when we get it into every research hospital that we connect to, that our national research and educational networks provide network connectivity for. And we will, for the next half a year, our short-term plan is to develop a multi-receiver so that you can have multiple streams coming into a single station. And another important thing for probably most of you, or quite a few of you, is we want to port the ultra-grid platform to Windows so that you have access to cards that are, especially to the cards that are supported nowhere else than on Windows. This is the case with the small box, which I was showing, the mini ITX box, which I was showing a few slides ago. Basically, it works perfectly. You can have one mini ITX i5 core PC with a graphics card through the PCI Express x16 slot. But you need a space for the capture card. And very, very nice capture card is USB 3 version of Blackmagic card, and it is only supported on Windows. So this was sort of the literal last drop that forced us to promise to try re-implement or port our software onto the Microsoft Windows platform. If you'd like to see any other functionality, please let us know. We'll consider it, and we'll probably do hard to get it in in our software. The software is available through the UltraGrid website. It's also now part of the Sage middleware platform as one of the core applications for high-quality video streaming and transmissions and interaction. You can have 1.5 release candidate 3 from the website. By the next week, we should have release candidate 4, so please test it. If you publish any paper, please consider referring to our work, which is available here, and I'd just like to thank you for your attention.
Are there any questions?
One question is, why not H.264?
Well, we were considering doing it, and we are still considering implementing the low latency mode of H.264. Currently, the reasons were twofold. First, Jpeg is simpler to implement, and second, we get complete frame independence. So if something happens to one frame during the transmission, which can happen over the network, we can correct it in the next frame. I mean, just a single dropped frame is usually not a problem. If we were using keyframe and progressive frames, which is what should be used if there is any advantage of H.264, if we drop the keyframe, we're out of luck for next few frames. So.
But you also have forward error correction, maybe.
Yes, yes, we do, but it's still probabilistic.
Yeah.
I mean, even the most advanced forward error correction schemes are not 100%. If you get like 30% packet loss, you would have real huge overhead to compensate for it.
And the second question is with respect to commoditizing and making this more widely available. So this so far, this is one could say proprietary. I mean that you have chosen a path of compression and the RTP payload and all that, which is a very good implementation. But this is what UltraGrid does. Nobody else can interoperate with that.
No.
The question is, let me just finish the question. The question is whether there's something that you could do towards interoperability. So someone could write a software which could, I don't know, do something with these streams.
Okay, so let me answer a couple of things. First, it's an open source software. So in this sense, it's not proprietary. Anybody can modify it, anybody can implement it, anybody can read it. Second, we have published the packet format. So this is openly available. It's part of the Cessna technical report. We're already considering pushing it through an ITF or something else to get it more as a more standard. We do implement various compatibility modes. So except for our own packet format, which was developed to be generic enough to handle both uncompressed and compressed video transmission at high packet rates, we can also support RFC 4175, which is the uncompressed, but it only works for uncompressed video. This is the problem, because for instance, this RFC relies on line numbers. Once you venture into the Jpeg compression, you get blocks. You no longer have any lines. So it wouldn't work like this. So that's why we suggested the new improved packet format, which basically is generic enough and provides strong enough numbering to ensure that we don't have frequent counter overruns. And third, it provides enough information for the receiver not to be configured, so that the receiver can auto-detect what's coming in and display the data accordingly. And we don't need to use any auxiliary channels. And we support IHDTV mode, so IHDTV compatibility mode. And as I've mentioned on the session yesterday, we're also implementing, as a testnet, we are also implementing an MVTP compatibility mode. But this is considered proprietary and will not be released open source based on some kind of business decision, which I will not venture into. Any other questions? Yep.
Could you tell me a bit about the congress, so what frame rate or
Yes.
resolution of camera?
Yes. We were using 1080i, 1080i at 50 frames per second. It's standard PAL world here. We were using Jpeg at quality 90, which meant with the multiplication of 2 and the images that we had there, it meant about 160 megabits per second for the primary flow, and about 50 megabits at quality 50 in a reverse direction. It's in the slides, in the schematics for your reference if you need to get back to it later. And it was quite important. The important thing here was to display the interlaced video properly. Because what we have noticed is if we de-interlace the video and display it through a normal computer display at 25 frames per second, the doctors were actually noticing that there is some flickering of the image if you have a camera panning fast, for instance. We can easily get rid of this using two things, or three things. We have a special filter that imitates the proper frame blending at twice the frame rate. Second, this is what we used for the conference. We output the video through the HDMI capture card so that it was feeding the projector with the interlaced mode. And the projector itself was taking care of appropriate deinterlacing, and it worked just perfect. And third way, we can also support 50 frames, full frames per second. If you take those small Panasonic cameras, TM900, and you connect them to Decklink Extreme Plus card, they can get, or we can get 50 progressive frames per second working. So this is the third way to get a smooth motion. So this is probably all that you asked for the...
Clear.
Yeah. Any other questions? More than happy to answer. Okay, so I'd like to thank you for your attention.
Thank you very much for this interesting presentation. I have several announcements for today.